Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we're going to talk a little bit about the four-color theorem, and while we're doing that, an intro to graphs, mathematically speaking, a little bit there. Now, inspiration for this is that this theorem was recently written about in Quantum Magazine. That's a math and science STEM magazine that sometimes pops up in some of my feeds. So I saw that article linked in the description below if you want to check out more with that. And this question has a long history. But it's based on a very simple question. How many colors are needed to color a map so that adjacent regions are colored differently? So I'll point out in the next example what we mean by adjacent a little bit more, or mention that. But roughly speaking, adjacent means regions that have an overlapping edge that they're next to each other with. So officially speaking, if they just share a point in common, they're not adjacent. We could talk about that more if needed, but that's the general idea. So really, you can walk into most elementary school classrooms and be inspired for this problem as well, because anytime you look at a map, this is where this type of question comes up. Right, so here we have a map of the United States, and if you look carefully, only four colors are used. And typically, right, the motivation of this is you want adjacent states to be different colors, so it's clear where one state starts, another one ends, things like that there. So just really quickly, if anyone's picky, if we look at the four states here, right? This is a famous point, the kind of four corners point there. Officially speaking, these two states back to back diagonally, right? So Arizona and Colorado, those are not officially speaking adjacent in that way. But here they are different colors, so that works out there as well. Okay, so let's move on then for a little bit of history. So what is the history of this proof? Well, it was first conjectured, right? That's an educated guess in 1852 by Francis Guthrie. Now, I want to talk a little bit about conjectures for things like this, right? This is something that you can do what might be called an engineer's proof, right? You can look at a bunch of maps, color them with four colors, and be reasonably convinced that that's correct. Does that mean that it's 100% true? No, right? That's where there's a difference between knowing something colloquially or knowing something kind of as general knowledge versus a true mathematical proof in that way. In the next couple years, some false proofs were given. And in 1890, one of the first big kind of jumps happened where Percy Haywood proved the five-color theorem. What is that? Well, you can color this with five colors instead of four. And a little bit of spoilers. We're going to do a little intro to graphs along the way. It took a long time to go from 5 to 4. So that is not just super simple decreasing that color by 1 in that scenario. So in terms of a more modern formulation, how would we typically think about this today? Well, a map would be what's equivalent to a planar graph. So first of all, what do we mean by a graph? Well, a graph is a collection of vertices, right? So we might have some vertices drawn in the plane, and we have edges connecting those vertices, right? So if we have these four vertices here, I could draw some edges connecting them, right? Maybe like this. And so you can think of this as telling you the information of, oh, for every state in our picture, what state is it next to? What state is it connected to there? And What is a planar graph? A planar graph is one that can be drawn so that no edges intersect when you're looking at this picture. And we'll come back to this a little bit later, right? But even if I add another edge here, this is clearly a planar graph. We have the 4 vertices, we have the edges drawn, there's no intersecting edges and things like that there. I will come back to this can be drawn in a little bit here as well. But for now, let's just think of it this way, and it should be pretty clear, but we will give an example with converting a map to a graph in a second as well. Now, what is the kind of coloring part, right? Given a graph G, its chromatic number is the minimum colors needed so that each vertex can be given a color different to any vertex it's connected to by an edge. So for example, if we just look at a very simple graph here, maybe we just look at a square with all of the edges connected along the way there, right? If this is our graph G, actually our chi of G, right? So this chi of G would actually be 2 in this case. Why is that? Well, because we have a square where the vertices, right, are just connected along the edges of the square. If I color this top left vertex green, the bottom right vertex green, and then the other 2 vertices blue, then clearly we have that colored with 2 colors, blue and green. Of course, those actual colors do not matter. And then anytime we have 2 vertices connected by an edge, the 2 ends of that edge are different colors. So in this case, the chromatic number or coloring number, if you just want to be a little bit more informal, would be 2. We can color that graph with 2 colors there. Now, let's look at an example of why maps can be thought of as these planar graphs. So let's go back to our states here, right? And let's kind of say, then, how could we turn a map into this graph? Well, first of all, let me kind of draw vertices for each state. So I'm going to use kind of orange and red, so it shows up a little bit different here. But right, we could, keeping these colorings even, draw all of our states with these different colors that we have there. So we have all of our different states. Each state is a vertex. Now, little geography, right? This state here in blue up here, Michigan, is in 2 parts, but it's 1 state, so it gets 1 graph vertex in that scenario there. And then, right, remember the edges are telling us when a state is connected to another state. So if we look at all of our states, right, I'm not really going to be naming them here, but every state just needs to draw an edge for whatever state it's connected to there. So anytime they share a bit of a border, we have to connect those states here. I'm going to try to be complete with how I draw this, but right, if I miss any, you can let me know in the comments below. But the more important thing is we kind of have the rough idea here. I also don't want to argue too much about how borders work, right? I don't remember where the US-Canada border is. I think we might say Michigan and Minnesota are connected via this top part. But again, this rough idea is what's more important in this case there. So we have all of these states, right, and where they connected in that scenario. Again, I'm going to show another example of this in just a moment. But I want you to realize at least that while a map might show us geography, things like that, a graph is more abstract. So as far as the graph is concerned, right, we're just talking about these states as, right, abstract things. our graph is drawing where the states are connected to one another there. And right, the reason for that is, right, it's this more mathematical thing. It doesn't affect our coloring stuff. But I just want to point out, as far as a graph is concerned, right, you might want to kind of change the graph to make it more readable or something. And this graph with moving around where the vertices are is exactly the same. The position of the vertices doesn't matter. Officially speaking, it's how they're connected to each other and stuff like that as well. Right? So let's look at that with a quick example here. Right? And it's just reiterating this fact that the position of the vertices and edges is not important. So let's look at a graph here. And I want to look at a simple graph with 4 vertices. And just to clarify things, right, I want to make sure we label those vertices. So I have A, B, C, D in this case there. And let's say that as far as our edges are concerned, A is connected to B, A is connected to D, D is connected to C, and C is connected to B. And the question I want to ask here is this graph planar? Right, and if you look at this, remember our definition of planar was something to do with no edges intersecting. So you might look at this and say, hey, the edges intersect, so our answer is no. I want to remind us, however, that we had this phrase can be drawn. This graph is planar, and this is where the ordering of those edges and their positions, right, amongst the vertices, right, it's just telling us what vertex is connected to what other one. So what if we swap the position of A and B? So instead of having A and B, what if I flip-flop those around? Notice then we can still draw in the same edges. The edges are just telling us connections. A is connected to B, B is connected to C, C is connected to D, and D is connected to A. So this answer is yes, because I can draw the same graph, right? So we're redrawing the same G. This is the same exact graph, because all a graph is a collection of vertices and edges describing what other vertices are connected to each other from there. So it's a little bit abstract, but you need to keep that in mind. There's actually some games like this where you have to move around the points to make it a planar graph, but that's kind of the idea for this planar graph. Can be drawn. Now, back to the proof, and then we'll give some questions for next time to wrap up. This full conjecture, like I said, it was a long time. It wasn't proven into the 1970s and 80s. Right? There were still some pushback of things that way as well. Some things were corrected. The 2 people credited with this are Kenneth Apple and Wolfgang Haken. They reduced the problem to, and this is where things are a little bit crazy or funny, they reduced it to 1,482 cases. Actually, the first draft had like 1,800, and then they said, oh, some of those are redundant. We can reduce it down further, still down to 1,482 cases. And they verified each and every one of them with the aid of a computer. And they published proofs along the way, but in 1989 they published a book, Complete Proof, with some corrections, and a 400+ page supplement with some printouts of all of these different cases that were helped by a computer to do. This is also interesting because it's one of the first scenarios. There was some pushback of this using a computer type stuff going on there. It's one of the first times that was happening in mathematics as well. Now, Couple of questions to think about for next week's video where we will answer these questions. Try to come up with planar graphs that have chromatic number 2, 3, and 4. Remember, every planar graph has a chromatic number that is 4 or less. That is the 4-color theorem. There could be some with smaller. And try to make these graphs as simple as possible. You've had some spoilers already today, but it's good to just think about those planar graphs there. You could try to make some more complicated ones if you want to as well. Now, want to do a little bit of a preview then as well of non-planar graphs. Try to come up with a graph with chromatic number 5. It will have to be non-planar, right? You don't need to worry about that so much though. So you can almost ignore that portion of the question, right? You can come up with a graph with chromatic number 5. By the 4-color theorem, it will have to be non-planar. You can do it with 5 vertices. And if you think about this a little bit more, your idea possibly for 5 vertices, I would say it's pretty likely that that same idea can be used to find graphs with chromatic number 6 or 7, however big you want there. Now, we will talk about this more next week, so stay tuned. Hit the like button, subscribe to our channel, make sure you get those updates. You can check out our continuation where we talk more about these questions next time. If you have any ideas for new topics, let us know in the comments below. Otherwise, thank you for watching, and I'll see you all next time. Goodbye.